All right. So we stopped at this point yesterday, where we were looking at stratification of aquifers. Uh, so in general, we were trying to understand how the effective hydraulic conductivity would be for an aquifer which has multiple layers of different thicknesses and with different hydraulic conductivities, right? So that is what we were trying to do. And when when the flow is parallel uh, to the layering, right? So if I have the layering of this kind, uh, oops, when I have the layering, let's say of this type, okay, I can have n number of layers, and if the flow is going parallel to the layers, right? Then I get this simple formulation for the equivalent hydraulic oops, I'm sorry. Okay, then I get this formulation for the equivalent hydraulic conductivity, which is simply sigma ki bi divided by sigma bi, right? So if I think of, instead of thinking of it as individual layers, if I look at it as one composite whole with an equivalent hydraulic conductivity, then that equivalent hydraulic conductivity will simply be given by this formula. This is if the flow is parallel to the layers. So now let's quickly try to understand how things would be if I had flow occurring perpendicular to the layers. Again, I have the same setup. I'll I'll do it for a simple case of two layers, and then we'll uh, extend the understanding to a general understanding of n number of layers. Okay, so suppose I have flow, sorry, going perpendicular to the layers. All right, so the flow is going past the layers in the vertical direction. All right, so now, so we'll have to break it down into two sets. So let us say the flow going in is at some flow rate q, okay, which we are going to assume is going to remain constant, right, across the layers. If you have to assume it's continuous flow, or if you're assuming that mass is being conserved, then the flow is happening at a constant steady rate. Okay, so this q as it flows into the first layer will be minus k1 times dh1 divided by b1. You agree with this? So in going from the beginning of this layer to the end of this layer, okay, so in moving from point 1 to point 2, there is a head loss of dh1, let us say. Okay, and what is the distance that has been traveled? The distance traveled is b1, the thickness of the layer, right? So this is what our expression would look like. So it's minus k1 times dh1 divided by b1. Okay, now the same flow is happening through the second layer, which is of thickness b2 and has a hydraulic conductivity of uh, k2. So it will be something like this: k2 times dh2 divided by b2. All right, this is the this I think nobody has a problem with this. Now I'll rearrange this a little bit. What I'm going to do is I will rearrange this in the following manner. Okay, so I'll say dh1 I'm sorry, dh1 will be minus q b1 by k1, and dh2 will be minus q b2 by k2. So the total head loss happening as I move through the first layer and the second layer, the total head loss dH is simply minus q times b1 by k1 plus b2 by k2. And if there are n other layers, you will simply add on plus b3 by k3 plus b4 by k4 and so on, right? So the total head loss that is occurring through this composite system is simply this, to this actual system is simply this. Now, if I replace this with an equivalent system, okay, which has a thickness of b1 plus b2, okay, and has an equivalent k, uh, right? So then for that case, the head loss will simply be minus Q into B1 plus B2 divided by K equivalent. Correct? If instead of having these separate layers, if I have an equivalent a layer, then this is what I would get, right? So therefore, if I equate these two terms, both these should be exactly one and the same. So therefore, I can write B1 plus B2 divided by K equivalent equal to B1 by K1 plus B2 by K2, right? In other words, let me since I don't have space, let me just quickly write this in short form. I hope you okay. I will write the generic expression K equivalent, or sorry, 1 by K equivalent equal to sigma Bi by Ki divided by sigma Pi. Have I got the math okay? The algebra is fine. 1 by K equivalent equal to sigma Bi by Ki divided by sigma Bi. Right? So this is the expression for the equivalent hydraulic conductivity in a direction perpendicular to the when the flow is happening in a direction perpendicular to the layering. The similar expression, if the flow is happening parallel to the layering, looks like this: K equivalent equal to sigma Ki Bi by sigma Bi. Okay, so now this is very interesting. Okay, so just imagine this. Just imagine that I have two layers with let us say K1. K1 is, let us say, it's 10 meters per day, and K2 is 0.1 meters per day. Okay, for the sake of simplicity, we'll give some simple numbers. Okay, I have 10 meters thickness, 10 meters thickness of an aquifer material of 10 meters per day, and 1 meter thickness of an aquifer with a hydraulic conductivity of 0.1 meters per day. So in the x direction, okay, so assuming that this is x and this is z, so the equivalent hydraulic conductivity in the x direction, what will it be? Can you just put in the numbers? It will be 10 into 10 plus 0.1 into 1 divided by 10 plus 1, right? So kx will be 10 into 10 plus 1, correct? Sorry, 0.1, 0.1 into 1. So it will be 0.1 K1 into B1 plus K2 into B2 divided by B1 plus B2, 11. What is this? 100.1 divided by 11. Right? So Kx is 100. I'll just ignore the, right? 100 divided by 11 is about 9 point something, right? Meters per day. Right? So if I'm interested in the horizontal hydraulic conductivity, when I have two layers, one which is 10 meters per day and the other which is 0.1 meters per day, still when I compute the equivalent hydraulic conductivity, I get something which is very close to this original 10 meters per day, right? This one gives me 9 point something, which is almost the same as 10, right? There's only a 10% difference. Now compute let's do the same thing for the vertical direction. Okay, so 1 by kz equal to, what will it be? 10 by 10 plus 1 by 0.1, right? Divided by, what will it be? 11, right? Can somebody just quickly compute this? 10 by 10 b1 by k1 plus b2 by k2 divided by 11. So what do you get? Divided by b1 plus b2. So this will be 10, 11, 11 by 11. What is that?
0.9.
0.1, right? So kz will be approximately 0.1 meters per day.
No, sir, 1.
What will it be?
Yes, fine.
Is it okay? Wait a second.
KZ is 1.
KZ will be 1 second. So the numerator will be 10 plus 1, 11. 11 by 11, so 1. Okay. You're right. You're right. Okay, so KZ will be about 1 meter per day. So you see what happens when you're looking at uh, vertical and horizontal flow. Okay, so typically when we deal with groundwater, we are more interested in horizontal flow than vertical flow. So this Kx is what we are more interested in. Now you see what happens because of the way this and the layering is, and because of the thicknesses and so on, the horizontal conductivity is always dominated by the layer which has the higher conductivity. Okay, the vertical is always dominated by the layer which has the lower conductivity. You understand what I'm saying, right? So therefore, I mean, you could do a similar exercise. I mean, I choose 10 and 1 meters. If I chose 10 and 10 meters, if both of them were of equal thickness, then you will see something very interesting. This kx will not change much. Kx will still remain about the same. What will be kx? Kx will be 5 meters per day in that case. It will be about 5 meters per day. But kz will be 0.1 if you do it for 10 and 10. Okay. So basically, what I'm trying to say is, when you're looking at flow parallel to the layering, the equivalent hydraulic conductivity is dominated by the one which has the higher of the layers. So if I have n layers, whichever layer has the highest number, highest value of k, your eventual equivalent k will be closer to that highest value. When you're looking at flow that's flowing perpendicular to the layers, the layer which has the least hydraulic conductivity will limit the equivalent hydraulic conductivity in the z direction. Okay, this is because of the way the expressions look. The expression gives more weightage to the lower ones for the vertical flow perpendicular to the layers, and the weightage is more appropriate to give weightage to the flow that is happening parallel to the layers in the case of the horizontal case. Okay, I know I'm confusing the issue a little bit. Maybe I'm not getting the words right, but essentially I think you understand this. So you can do this computation for any number of combinations. You play with this, try different values of k1 and b1 and see what you get for kx and kz, right? You will notice that kx most often will be closer to the highest k in the different layers. I just did it for 2 layers. You can have n number of layers and try it. And kz will most often be closest to the lower number. Okay, because when you're having flow happening perpendicular to the layers, the one which stops the flow is going to have more weightage. Whereas if I have flow perpendicular to parallel to the layers, then the layer which has the higher k will have more predominance. Just imagine this. Imagine that there's a highway. Okay, maybe a highway example would be good. Okay, imagine I have a highway or a lane. Okay, there are 2 lanes on the road. If you're trying to go along the highway, okay, you will automatically move to the lane which allows you to go faster, right? You will not go to the lane where traffic is moving slowly. If there are multiple lanes, if you're trying to come here, you find out that this lane is slow, you just quickly transition to this, and then uh, you take the path of least resistance, right? Water also does the same thing. Water will always follow the path of least resistance. Which is the path of least resistance? Whichever allows you to flow easily. So it will take the equivalent k will always be closer to the layer which has the higher k. But if you're trying to go across the road, just imagine you're trying to cross the road. Okay, the rate at which you cross the road, what does it depend on? It depends more on the place where the traffic is going very slowly, because you have to wait for the traffic to clear there, and only then you can cross the road. Where it's going fast, right? You may find a gap between 2 vehicles, and then you may just cross. Okay, this analogy is not perfect, but I'm trying to tell you what it is, right? So you may get past this this lane very quickly. Okay, but because here the traffic is all moving slowly, you will have to wait until the traffic clears, and only then you can go across, right? So this layer will determine how long it takes for you to move across. Whereas if you're flowing along with the traffic, the faster lane will determine how long it takes for you to go, right? It might not be a perfect analogy, but I think you appreciate what I'm trying to get here. Okay. Any questions on this? All right. Okay. So now let's try to solve one simple problem on the concepts that we've discussed so far, and then we'll move on. Okay. So let us say at a certain point in an unconfined aquifer of 3 kilometer square area, the water table was at an elevation of 102 meters. Due to natural recharge in a wet season, its level rose to 103.2 meters. Okay. A volume of 1.5 million cubic meters of water. So this capital M refers to million cubic meters, right? So M, capital M meter cube is million meter cube. A volume of 1.5 million cubic meters of water was then pumped out of the aquifer, causing the water table to reach a level of 101.2 meters. Assuming the water table in the entire aquifer to respond in a similar way, estimate A, the specific yield of the aquifer, and B, the volume of recharge during the wet season. Okay. So is the problem statement clear of what we are trying to achieve here?
Yes, sir.
Okay. So now let us try to understand what do we need to do, or how do we? So the first part, let's look at the first part. How would you estimate the specific yield of this aquifer? Remember what the specific yield is. Specific yield is if the water, if there's a unit decline in the water level or the water table over a unit area, whatever volume is released from the pores, overcoming the forces of intramolecular attraction and so on, that portion is the specific yield, right? So just imagine I have an aquifer, okay, like this. Okay, imagine that there's a box. Okay, in reality, it's not like that, but we'll just imagine this box has a surface area in this case of 3 kilometers square. 3 kilometers square, and there's some recharge happening into this because of rainfall and so on. Okay, and then there's also pumping happening out of this. So I have the water table initially at some level. Okay, just think of it like an entire box that responds uniformly. Okay, due to natural recharge, its level rose. So after recharge happened, the water level rose to some level over here. Okay, and then some volume of water was pumped out, causing the water table to reach an elevation of 101.2. So then some pumping was done and the water level reached somewhere over here. Okay. What is the specific yield? Right. So the specific yield, if you remember, specific yield is volume of water drained out per unit area per unit decline in head. Okay. So now here, this is the volume of water drained out per unit area per unit decline in head. Now here, the total area is given and the total decline in head is given. So if a unit area and a unit decline causes S subscript Y amount of water to drain out, how much uh, SY would result in a decline of how much is it? 103.2 minus 101.2, right? So the water level reached 103.2, and then 1.5 million cubic meters was taken out, and the water level came down to 101.2. So the water level has declined by 2 meters over an area of 3 kilometers square, right? And we have obtained 1.5 million cubic meters of water from that. So therefore, the specific yield must be. So you can, I think you should be able to solve this, right? So the volume of water drained will be equal to specific yield multiplied by area multiplied by decline, right? Because the specific yield is the volume drained out per unit area. You multiply it by the actual area, you will get the volume over the entire area. And this specific yield is also the decline per unit decline in head. You're given the actual decline in head. So you can simply solve for it, right? So it will be 15 into 10 power 6 meter cube equal to SY into, what is the area? 3 kilometer square. 3 into 10 power 6 meter square into, what is the uh, decline in head? So it went up to 103.2. After that, 1.5 million cubic meters of water was pumped out. So this 1.5 million cubic meters of water pumping out caused the water level to decline from 103.2 to 101.2. So the decline is 2 meters. Sorry. I think you might have lost the screen. 1 second. Just a second. Okay. So this will be 2 meters. So can you quickly solve for specific yield? What do you get?
Sir,
Yes.
so the volume should be 1.5 into 10 to the power 6, right?
Oh, I'm sorry. I wrote 15. I'm sorry. 1.5. 1.5 into 10 power 6. So 10 power 6 goes out. So it will be 1.5 divided by 6. Right? What is it? Quickly.
0.25.
All right. So the specific yield is 25. Now remember, specific yield doesn't have units because it is volume per unit area per unit decline in head. Right? So it's volume of water drained, which has units of meter cube or length cube per unit area. So that's divided by L square per unit decline in head. So that's one more divided by L. So you have L cube per L square per L. So therefore it becomes unitless. So you can say, when I say the specific yield is 0.25, that means from this aquifer, you will get 25%, right? 25% of the porosity will drain out, right? 25% of the porosity will drain out per unit area per unit decline in head. No, not 25% of the porosity. I'm sorry. Yeah. So usually the porosity will be, okay. Let us say porosity is, let us say the porosity in this case is 0.4. Yeah. Out of the porosity of 0.4, 0.25. So percentage you can compute whatever, right? So 0.25 out of the porosity of 0.4. Assuming the porosity is 0.4, it could be anything. It could be 0.3. It could be 0.35. Whatever it is, right? Whatever your porosity is, out of that 0.25. I won't say percentage, that's incorrect. Okay, so 0.25 out of a porosity of 0.4 will get drained out from your from this aquifer if there is a unit decline in head over a unit area. All right. Okay, so now let us look at the next part of it, the volume of recharge during the wet season. So if this is the specific yield, how much recharge must have happened to cause the water level to rise from 102 to 103.2? Okay, so the second part is exactly the same as the first part. So here it will be volume of water recharged will be equal to specific yield into area into rise, right? So if the water level rises from 102 to 103.2, so that's a rise of 1.2 meters. So you are asked to find out what is the volume of water recharge. So it will be equal to specific yield 0.25 into 3 into 10 power 6 meter square into 1.2 meters, right? How did I get this 1.2? The water level rose from 102 to 103.2. So that's an increase of 1.2 meters. So 1.2 into 3 to 10 power 6 into 0.25 will be the volume of water that has been recharged. All right. Okay.
Yes, sir.
All right. Okay. So we'll quickly move on to now. See, so far we've been talking about the aquifer from the perspective of the flow happening in it and so on. I'm sorry, the perspective of the properties and so on. Now we're going to talk about if we are looking at a given aquifer. Let us assume I'm looking at a confined aquifer. Okay, and I want to understand what are the equations that govern the flow inside a confined aquifer? Okay, so we will begin with a very simplified case, or kind of like a hypothetical case. So imagine I have the land surface over here. So this is the land surface. All right. At some depth, I have a confined aquifer. Okay. So this, whatever shaded, line that I'm drawing, that indicates that this is a confined aquifer, which does not get any water from above or from below, right? So it's like a sandwiched, it's like a unit sandwiched between a confining unit above and a confining unit below. Okay. And let us assume that the thickness of this aquifer is constant. Okay. And it has, hydraulic conductivity of K, which is uniform throughout the entire thickness and throughout the entire length of this aquifer. Okay. So if on one side, okay, let us say I have some big river on one side of this, on one side, and another big river on the other side of the, okay. So let us say here, the water level is somewhere over here, and here the water level is somewhere over here. Okay. So let us say I have some, let us say the datum is over here. Okay. For the sake of simplicity, we'll assume that this is my datum. Okay. So if you think of this as a system like this, where the coordinate starts where this aquifer starts. So the aquifer starts at x equal to 0, and it extends for some distance x equal to L. I'm sorry, I have a little bit of a cough today. So let's say this distance between the two surface water bodies is capital L. Okay. So at x equal to 0, I have one river, okay, which is connected to this confined aquifer, where the water level in this river, let us say, is H0. Okay. And on the other side, I have another river whose water level is H subscript capital L. So H0 at x equal to 0 and HL at x equal to L. These are the boundaries to this confined aquifer. Okay. So now you can clearly see I have a confined aquifer where there is a gradient between the two ends of the aquifer. I have a water level of H0 at one end and a water level of HL at other end, where H0 is greater than HL, right? So now clearly you can see that there is going to be flow happening in this aquifer in this direction. Does everybody agree with that? The flow will happen from this first river to the second river,
Yes, sir.
right? So now my question is, how do I find out how much flow is happening? That's one thing. And the other thing that I'm interested in is, let us say I'm at some point in the aquifer. Let us say I'm at this point over here, and I ask a question: what is the piezometric head? Right? You remember piezometric head? I mentioned this terminology before. Piezometric head, or sometimes it's also called potentiometric head. Okay, this is basically P by gamma plus Z. But we don't worry about P by gamma plus Z, we just call it H. Okay. What is the head in the aquifer? Sometimes we even ignore this piezometric, potentiometric, we just say head, with the understanding that it is the total head at any given point in the aquifer. If I ask a question, at some point in this aquifer, in this confined aquifer, what is the head in the aquifer? If my question is that, okay, I should be able to solve for that and try to find out what the head at any point in the aquifer will be. Now, if I tell you, let us say at x equal to L by 2, intuitively, can somebody tell me what h the head will be? At x equal to L by 2, right in the middle between these two
H naught
curves.
HL by 2.
What is that?
Like H naught plus HL by 2.
H naught plus HL by 2. Okay. Does everybody agree with that? H naught plus HL by 2. I don't know. The algebra doesn't seem to. Will it be no? It will be HL plus. Oh, maybe the algebra works out fine. Yeah, I'm not used to referring to it that way. H naught plus HL by 2.
The average of 2.
No, wait a second. If you say that, then you're saying the head between these in the middle will be greater than H naught. H naught plus
Yeah.
HL by
It
2.
won't be greater than S naught. How can
Huh,
it be greater than S naught?
you tell me.
H naught plus HL by 2 will obviously be less than S naught.
Huh? How will H naught plus oh, H naught plus HL, the whole thing divided by 2. Oh, okay, that's what you're saying. Okay. H naught plus HL divided by 2. Huh, okay, now it makes sense. I thought you were saying H naught plus HL divided by 2. H naught plus HL divided by 2.
Both.
Okay,
Both.
fair enough. See the perils of online teaching. Okay, all right. So intuitively that seems to be all right, right? But you have to prove it. You can't just say something like that, right? So then I would say, let me try to understand from first principles. I know already, even without doing anything, I know that flow is happening from H naught towards HL. Okay. So what I'll do is I will pick at some arbitrary X, I will pick an infinitesimal volume, okay, and do a mass balance for this. Okay, so I'm going to draw this shaded area over here. At some, this is at some random X, I've picked up an infinitesimal volume. This is at X, the other end is X plus delta X. Okay, so what is the flow coming into this and the flow going out of this? Our usual mass balance approach that we did in fluid mechanics. Now we're just extending that to a confined aquifer in a underground. Okay, so at some distance X, let us say the discharge, the flow coming into this is let us say Q. This is our RC velocity multiplied by what should I multiply it by to get it converted into discharge?
Area.
Area. Now, what is the area of cross section of this infinitesimal slice? It will be in a direction perpendicular to the screen that you're seeing, right? It will be perpendicular to the screen. So we will imagine a unit thickness in the direction perpendicular to the screen. And what is the other dimension?
B.
B. The thickness of the aquifer will be. So if I multiply it by B times 1, which is the unit thickness in the direction perpendicular to the board, so you will ignore that. Q times B is the flow that is entering this infinitesimal volume at cross section X. Now I go to cross section X plus delta X. Okay, what will be the flow at this cross section? Can anybody tell me quickly? Taylor series. Let me write it. I don't have time today, so I'll
Dou cubed.
dou Q by dou X times dx. So this is the discharge multiplied by B, same B, no issues. Right? Is there any other flow coming into this elemental representative volume that we have picked up? We are assuming that this aquifer is infinite in the direction perpendicular to the board. Okay, so there's no flow coming in any other direction. And if you remember from this figure, you can see this is a confining unit above it and a confining unit below it. So there can be no flow coming in here or going out. Nothing is coming in from above, nothing is coming in from below. So these are the only two fluxes entering or leaving this particular control volume. Okay, so then I will write a simple expression. So what is coming in is positive, what is going out is negative, right? So it will be Q times B minus Q plus dou Q by dou X times delta X times B equal to this much is coming in, this much is leaving. Must be equal to what?
Storage.
Storage. Okay, so now let me add one piece of information. Maybe I should have mentioned that a little bit earlier. The river, the level H naught and HL are assumed to be constant. They are not changing with time. Okay. The rivers are flowing at some level, H0 and HL, massive rivers. Imagine that these are huge rivers. Okay. So this whatever flow is going into the aquifer is not changing the water level in the rivers at two ends. So will the water level in the aquifer change with time, or will it remain constant for all time? There is nothing coming in from above, nothing coming in from below. All that this aquifer only has two sources of water, or two connections to any other surface water body or anything else. One is a river on this side, one is a river on the other side. These two rivers, the water level is not changing as a function of time. So will the water level in the aquifer change as a function of time? Yes or no?
No, sir.
It won't change because there's nothing to change, right? So all right, so the right hand side is one big fat zero. Nothing is changing. So maybe I could have qualified this by saying steady flow in a confined aquifer, but it's useful sometimes. We just understand this from by doing it. Okay. Anyway, so now look at this equation. What goes out? Q times B minus Q times B goes out. So I'll be left with minus dou Q by dou X into B times delta X equal to 0. Right? This B and delta X are non-zero quantities. So dou Q by dou X must be equal to 0. Which in other words, what is Q? Let's think back what to our Q was minus K dou H by dou X. That was Q, correct? So if I put that in over here, I'll get dou by dou X of K dou H by dou X equal to 0, which in other words, assuming K is homogeneous and constant throughout the entire aquifer, you will get a nice, simple, beautiful equation. Dou square H by dou X square equal to 0. That's it. This is the expression for how the head varies in this aquifer as a function of distance x along the aquifer. Now, clearly you can solve this equation very, very easily. Not at all difficult. You integrate this equation once. Sorry, what is it? Integrate or differentiate? Integrate. Yeah. So you'll get dou H by dou X equal to C1. You integrate it again, you'll get H equal to C1x plus C2. Can you solve for C1 and C2? Can we solve for C1 and C2?
Yes, sir.
How do we solve for it? We apply the boundary conditions.
Yes,
We know the value of H at x equal to 0 and at x equal to L. You have two unknowns, two equations, solve for it. So you will get, so at x equal to 0, H equal to H naught. So C2 will be equal to H naught, right? C2 equal to H naught. Then you put that in again. I think you will get an expression that looks like this. H equal to H naught plus, what will it be? HL minus H naught divided by L into X. This will be my final expression.
yes, sir.
Right? You can do a quick check. Put x equal to 0 here. What do you get? H equal to H naught. No problem. Put x equal to L. What do you get? H naught plus HL minus H naught. HL. Right? So this is so it's a simple linear equation. Right? So it will simply be the head inside the aquifer will be represented by, I'm going to draw this dotted line. Okay, of course, I've not drawn it perfectly, but that's how the head varies in this confined aquifer as you go from the boundary on the left, which is at H naught, to the boundary on the right, which is at HL. Okay, very, very simple. No complication at all. So this is flow in a confined aquifer, and this is the equation. This equation, I don't know if you have heard about this. It's what is called the Laplace equation. You might have heard this in your, if you've taken a mathematics class, you might have heard of the famous Laplace equation. So this is a Laplace equation for flow in a confined aquifer at steady state. Okay, so this is steady state equation. This is what you get. All right. So now we'll do the exact same thing for an unconfined aquifer. Okay. In the unconfined aquifer, there's one additional level of complexity that is introduced. I'm going to try to do it quickly now because we only have about 10 minutes left. So let me try to draw it quickly. So I have a river on one side. I have the land surface. I have the other river on the other side. Same story. H0 on one side. HL on the other side. Then I have the bottom of the unconfined aquifer. Let's see. Which is completely, and then I also have the recharge coming into the, because it's an unconfined aquifer, it is exposed to the water table is exposed to the atmosphere, right? So I may have some recharge coming in. Typically we use capital R to represent recharge. Okay, so assume that this is my aquifer which has a constant hydraulic conductivity K, which is not changing as a function of X. Okay, so this is X, this is X equal to 0 to X equal to capital L. Okay, so now we do the same thing. We pick one, okay, I'll draw one infinitesimal cross section at some distance X in this unconfined aquifer, and I try to do the mass balance for that. Okay, so this is my infinitesimal volume. I have same thing Q. Now what do I multiply it by? In the previous case where there was a confined aquifer, I multiplied it by capital B, which was the thickness of the aquifer. Here, the thickness of the aquifer depends on where the water table is, right? So wherever the water table is, that is where that is the thickness. So for example, and let me just draw one possible. So this is just a random thing that I'm drawing. This is not the correct solution. So I've just drawn a kind of like a straight line similar to what we had before. Okay. So now what will the saturated thickness be here? The saturated thickness, let us say, it is at some value H at X, and then at X plus delta X. Let's write this term a little bit later. Let's write the other term. What is coming in from the top? It will be R times what? Assuming a unit thickness in the direction perpendicular to the screen, what will be R times? Quickly.
Delta X.
Delta X, thank you. Okay, so R times delta X is coming in from the top. Q times H is coming in from this left. And what is leaving is Q times H plus dou Q. Oh, we have to be a little bit careful here. Dou Q by dou X. No, wait. I'll do it very, very carefully. Can't afford to be careless here. Okay, so it'll be Q plus dou Q by dou X times delta X multiplied by, now what is happening to the H? H was some value over here. When I move a certain distance X, look at what is happening to H. H is also changing. We don't know by how much, but it is changing. The value is H over here, the saturated thickness. When I move a certain distance delta X, that saturated thickness is also changed. So it has become some new thickness, a new saturated thickness. So which I'll represent as H plus dou H by dou X times dx. Okay, so now have I accounted for all the terms? At the bottom I have an impervious membrane, so nothing is coming in from the bottom surface. There's an impervious surface there. Okay, so now I'll write my equation. Q times H minus Q plus dou Q by dou X times delta X times H plus dou H by dou X times delta X plus R times delta X equal to 0. Right? I hope there's no problem so far. So Q times H, there's going to be a Q times H over here as well. So that Q times H will cancel out. So I'll be left with minus Q times dou H by dou X times delta X minus dou Q by dou X times delta X times H minus dou Q by dou X times dou H by dou X times delta X square plus R delta X equal to 0, right? I think you should be, you understand what I've done exactly. This Q times H minus Q times H, it's cancelled out. So I'm left with Q times dou H by dou X, that's the first term, times delta X, minus dou Q by dou X into delta X times H, minus dou Q by dou X into dou H by dou X into delta X square. Now naturally delta X square is very small, so I ignore it. This entire term goes to 0. If delta X is small, then delta X square is even smaller, so that term goes away. So then I'm left with, let me try to write this in shorthand. So I'm left with Q times dou H by dou X plus H times dou Q by dou X equal to R. Does everybody agree with this? What I have done? This plus R on this left hand side goes to the other side, becomes minus R. Then you will have a minus and a minus and a minus on both sides. So the minuses on both sides go away. So then this equation, you can apply chain rule, right? So it's dou by dou X of Q times H equal to R. Correct? So if I apply chain rule to this, I'll get this. Yeah,
Yes.
is there a question? Yeah, so in the interest of space, let me try to squeeze it in over here. So it'll be, so this will be dou by dou X of H. I'll take the minus sign out because Q is minus K dou H by dou X, right? So I've taken the minus sign out, equal to R. So far, no issues, I hope. So this, okay, I'm going to take the K out because it's not a function of X and take the K to the other side. So this will become dou by dou X of H dou H by dou X equal to minus R by K. Agreed? The minus has come from this side to the other side and the K has come out of this and then gone to the denominator on the right hand side. Now look at this. Now I'm going to write this term as, okay, maybe I'll use this, right? H dou H by dou X is equal to dou square H square, sorry, not dou square. Does everybody agree with this? What is dou by dou X of H square? It will be 2H dou H by dou X. So I've divided by 2. So this is okay. Dou H square by dou X will be 2H dou H by dou X. But what I have here is only H dou H by dou X. So I divide by half. I divide by 2. This is okay. So then,
Yes.
yeah, so then this will be dou by dou X of half dou H square by dou X. So now kindly bear with me. So it will be dou square dou H square by dou X square equal to minus 2R by K. Okay. So this is the governing equation for head in an unconfined aquifer under steady flow conditions with two rivers on both sides with, whatever, with varying levels, right? If recharge is equal to 0, what will happen? If there's no recharge happening?
Then it's a confined aquifer.
No, it's not a confined aquifer. Then it's dou square H square by dou X square. Go back to the previous one. Confined aquifer is dou square H by dou X square.
Okay.
Okay. So confined aquifer and unconfined aquifer behave very, very differently. Okay. So anyway, so I don't want to, bore you by solving this, applying the boundary conditions and solving it. You can very easily do it, right? So you integrate this once, you will get dou h square by dou x equal to minus 2 rkx plus c1. Then you do it one more time, you'll get h square equal to whatever. Then you will have two constants, c1x plus c2, whatever it is. And you just simply have to apply the boundary conditions and get the values of that C1 and C2. I will leave that to you as a, kind of like a homework thing. Okay, is this okay? Okay, I think I had one. Yeah, okay. Yeah, I'll just talk very briefly about why is this even needed? All of this fancy equations and all that I'm writing, right? After I write this equation is not the end. Okay, you will have to apply the boundary conditions and solve, get an equation for h square. You'll get an equation for h square equal to something, 2r by k times x square plus something times x plus something. Okay, maybe I've even got the signs wrong. There might be a minus over here, whatever it is. Okay, you just have to solve for it. It's not a big deal. So this is your final expression. Now, why would this kind of thing be needed for a civil engineer, for example? Okay, now just imagine that you've all heard about the construction of all of these, what are they called, the metros in the different cities all over India, right? Now, as long as the metro is constructed above the land surface, there's no problem. But in a lot of cases, the metro is sometimes constructed underground, right? So you all must be aware of it. The metro is sometimes constructed underground. Now, whenever it is constructed underground, then if I have an aquifer where the water table is relatively high, then that will add some additional pressure to your underground metro and so on, right? Subway structures that you're going to be constructing underground. Now, for that, what is typically done is during construction, this could even be for not just for a metro. I'm just giving you the extreme example of the metro. Even if you're constructing an underground basement, for example, right? So you're constructing a basement underground, while you're doing even when you're doing the foundation work and so on, if the water table is too high, once you cut into the soil, if the water table is high, it will start, your entire construction area will get flooded with water, right? So have you heard of this phrase dewatering in your soil mechanics class or something like that? Dewatering. Okay, so imagine I have a construction site. This is plan view. Okay, in plan view, let us say in cross section view, let us say it looks like this. I have to build my foundation here, right? So first I excavate this portion and I start to construct my foundation and so on. But if the water table is over here, what will happen? The water will just start seeping into your construction area, right? If you want to put concrete over here, you can't have water just draining into your area. You'll have to somehow drain this water out so that your construction area is dry, right? So what is done is, typically you will have a trench around your uh, uh, construction site. This area you want to keep it dry, so they'll dig a trench, maybe even a deeper trench. I'm just drawing it for, and then you will install some pumps over here, which will pump out the water. Which will pump out the water, not in this direction, in this direction. Okay, so that your construction area remains dry. Now, to decide how deep your trench has to be, or how much water you need to pump, and so on, you need to know how to provide these drains. So that's why I'm given this title, provision of drains. So if you want to provide a drain such that your construction area remains dry, you need to know, what is the underground aquifer like? Is it an unconfined aquifer? What is the recharge rate? What is the hydraulic conductivity? How far should I space these drains out? Okay, I'm just showing a cross-section view, but you may need multiple such trenches which keep pumping water out. So even now, today, if you go to any of the construction sites, when they're doing foundation work, typically they'll have a small drain there, a small pump sitting there, which will be pumping out water so that the construction area can remain dry. Okay. So this is what I mean by the provision of drains. So you may need to do what is called dewatering to ensure that your construction site remains dry. Now, this is also used sometimes, if you're a farmer, for example. Okay, some crops do not, for example, if you look at paddy, for example, paddy typically you might have seen these images of a paddy cultivation happening. I realize that I've gone over time, but I think it's lunchtime now, so just give me a couple of minutes. Okay, I'm sorry. Okay, what was I saying? So paddy, for example, requires water to be completely saturated, flooding. It's called flooding irrigation. But some other crops don't like water at all. Okay, you have to only provide water at a specific time, and the soil should not get waterlogged. So for those kinds of crops, if the water table is high, right, the farmer, what they will do is they'll set up a small drain around the farm so that the soil never gets completely saturated with water and never gets waterlogged. Okay, so this can even be done for farming. Farming operations may require that soil does not get waterlogged. Soil does not get waterlogged. Okay, so these kinds of drains are also provided in farms. Okay, in a small farm it might be it might be a little bit of a challenge to do this, but if you have a relatively big farm, then it's you can accurately calculate how deep the trenches need to be so that you can drain the water out, at what depth you need to place these drains so that the water drains out and doesn't end up flooding the farm and so on. Okay, so there's lots of applications for this. Okay, so we are not doing this as some kind of a mathematical exercise to find out what what the head in an unconfined aquifer is, or the head in the confined aquifer, not so much. Unconfined aquifer has lots of practical applications. Confined aquifer was just because it's easier to understand the confined aquifer. The unconfined aquifer is a little bit tricky, so I began with the confined aquifer and then we came to the unconfined aquifer. Okay, any questions? All right, so next class we will kind of wrap up with groundwater. We'll just have one or two topics that I want to cover. I'll try not to get into too many equations and stuff, maybe one or two equations, and then we'll wrap up the semester. So we are at the end. So next week, next Thursday is the exam. I'm sure you must have seen the timetable. So do not worry about it. We'll discuss a little bit about the exam in the next class. All right. Thank you very much, and stay safe. We'll meet on Thursday.